Hi, my name is Balazs Udvarhelyi, and the title of this talk is on the security of off-the-shelf microcontrollers. Hardware is not enough. So this work had been done at UC Louvain, and I will start by the table of contents, which will be followed by the small introduction and the presentation of the targets and the measurement setup. Then I will have a small overview on common detection and evaluation tools and a presentation of the one-hot TVLA. Then we will use these tools to infer the architecture of the selected targets. And then finally, we will end the talk by presenting some attack results and some discussions on them. So to start the introduction, I would like to highlight the way side channel attacks are investigated differs between the academy and the real-world commercial applications. Indeed, the academy provides mostly well understood and controlled environments, which is not the case of real-world targets. And as a result, we observe that published attacks on the real-world targets are much more sporadic. Still, we have some examples. We had attacks on SIM cards, we had attacks on the Xilinx bitstream, and we also had attacks on smart lamps. We also observed that there's a common recurring effect in these published black box evaluations. That is, there's a first step, which is that a heavier reverse engineering effort is needed, and only with the sufficient understanding that this reverse engineering provides, we can perform attacks. However, we also observed that these attacks were relatively easy. Indeed, it turned out that the implementations of these previously cited papers turned out to be unprotected. So this led to a research question, which is how much does obscurity help in the case of unprotected coprocessors? So to answer this, we provide here a case study with two AES-128 coprocessors from two well-known manufacturers. We have ST Microelectronics and NXP. We also show that simple attacks can be successful, even with the limited initial understanding of the architecture of the coprocessors. And this has been done with using mostly standard tools and some less standard ones. We have here the one-hot TVLA that we will present later, and the continuous wavelet transform. So let's continue with the presentation of the targets, where we have on the left the NXP Kinetis K82 MCU, which has an ARM Cortex-M4 processors, and two cryptographic cores were provided, one of which is the LP trusted cryptography core, which we chose to attack because it mentioned a side channel countermeasure that is presented on this slide. So we have this is an excerpt of the reference manual of the NXP. So the DPMax seed register is used to reseed the mask that provides resistance against differential path analysis attacks on the AES keys. So this countermeasure will be studied later on. So this was for the NXP, and on we have the STM on the right side, which is an STM32L4 series MCU, which also comes with an ARM Cortex-M4 processor. And in this case, we only had one AES peripheral without any side channel countermeasure mentioned. So for sampling, we used the Picoscope's 5000 series USB oscilloscope, and we used it at 500 megasamples per second at 8-bit resolution. We sampled both EM leakage and power leakage at the same times. For EM leakage, we used an H-field probe. And for power leakage, we used a 10 ohm shunt resistor in the case of the NXP. We clocked the MCUs at 8 MHz, 80 MHz, and 100 MHz. And here is an exemplary leakage of the NXP at 8 MHz with EM leakage. So now I will continue with an overview of some common detection tools. So we here have on the left non-specific tools like the non-specific t-test, which have the advantage of requiring a small number of classes to be estimated and therefore provide a fast leakage detection. On the contrary, we have on the right specific tests, like we can have as an example the SNR, which need to have all the classes to be estimated, but provide on the contrary PY detection, which is not possible with the non-specific t-test. So our objective was to have the best of both worlds. We wanted to have a low number of classes to estimate, and we still wanted to remain specific. So in this case, we have some examples. We already have the semi-fixed versus random t-test, which is a t-test that becomes more specific as the number of classes increases, but however is model dependent. Our tool is the one-hot TVLA, which we'll present on the next slide, which has the advantage of being specific at some point of the encryption and non-specific elsewhere. And this is done with only 2 classes per byte. So the one-hot TVLA is indeed 16 well-chosen fixed versus fixed t-tests, and we chose the inputs to have a single byte difference in the first round of the AES. So our objective is that the one-hot TVLA is specific for the first round of the AES. And this is done by using only 17 sets of traces. So to construct the sets of traces, we first have a reference set. Then we take 1 byte of this reference set and change it to another one. And then this is the construction of set 1. So we can see that only byte 1 differs in this case, and we choose to do a t-test on these 2 sets. Then we take again the reference set and change byte 2 this time. So in this case, we have only byte 2 that is different, and we choose to do a t-test between reference set and the set 2. So in this case, we can see that we only need to do 17 sets of 17 sets of choices to do the 16 t-tests. So how does it compare to other tools that we use, like the signal-to-noise ratio? So on the left, we have the one-hot TVLA, which still has the advantage of being able to identify the points of interest. It still has the advantage of being low on memory. Still, as a t-test, it can have some false negatives. On the contrary, we have the signal-to-noise ratio on the right, which has the advantage that we cannot have with the one-hot TVLA, is that SNR peaks are do have a quantitative value, but we do this at the cost of estimating all the classes, so the 256 per byte, and we also need to sample more. However, we use the one-hot TVLA and the SNR as a complement, and they do complement well each other, as we will see on the next slides. So now we will apply the tools that we presented. So we start by the one-hot TVLA. So here is a result of on the NXP Kinetis device with EM leakage, and this is the t-test where byte 4 was different. So we can first see that there is a non-leaking part with still some leaking points, and there is a very well leaking part, which is the end of the encryption. So we can identify 3 elements here. The first one is the loading of the plain text. The second one is the key addition. The third and most interesting one for us is the S-box output. And then we come to the non-specific part of the t-test, which is where we observe leakage basically everywhere. So the t-test is in this case indeed specific for the first round and non-specific afterwards. So now we will take the samples that we obtained here at the peak of the S-box, and we will perform an SNR around those. So here are our results. So the main conclusion here is that every byte is detected. There is some difference in the SNR levels between the bytes, but nothing much. And we observe 1 cycle per AES byte. So that's it. And we also observe that power leakage spans over multiple cycles, which is not the case of the EM leakage, which is more precise in time. So here is the SNR graph of the first and second round. The interesting part of this graph is to show that there is no loss cycles between the first and second round, which means that the operations, the other operations such as the mixed columns, shift rows, key addition, etc., are performed in parallel to the other boxes. Finally, we conclude that the architecture of this NXP device is one cycle for each S box, and therefore this is serialized on 8-bit S boxes. So we jump straight to the attacks because we observed a very similar effect architecture on the STM device. So to present the attacks, I will first start to present our attack strategies. So we had the first step, which was the architecture inference with the one-hot TVLA, and then we either perform SNR directly in the time domain, or we perform the continuous wavelet transform on the row traces, and then we perform an SNR in the wavelet domain. Either way, we perform then a pairwise selection based on SNR thresholding, so we keep all the same poles above the noise floor, and then we do two attacks, either CPA or template attack. For the template attack, we use the principal component analysis to further reduce down the number of dimensions that corresponds to the number of dimensions of the template attack, which was 5 in this paper. So all the attacks that we show are showed with a profile leakage model, so even with the CPA. We also performed the simpler Hamming weight and Hamming distance leakage model CPA attacks. Those were also successful, but were way outperformed by the profile attacks, so we chose to only present the results of those. So on this table we have the results of the attacks on the NXP Kinetis device. We can see that to obtain a 2 to the 32 key rank, we need only 1,200 traces at 8 MHz, and we need almost 3 times more, more than 3 times more at 100 MHz. And the leakage models, the leakage used are also not the same, and the attacks are different too. On the case of the STM32, we observe much less difference. The best attack is provided with the power leakage and the continuous wavelet transform, and at 8 MHz it only needs 1,800 traces, and the same at 80 MHz only needs 1,600 traces. So now let's have some discussions on first the attack strategies. So we have the attacks that we used. We had template attacks and CPA. So we observed that the best results were mainly obtained with the CPA. In fact, only the NXP at 8 MHz had best results with the template attack. So we conclude that this is still device dependent, but we have an idea is that the multiple dimensions of the template attack needed providely a more higher profiling effort, and that if we do this higher profiling effort, the template attack should at least reach the efficiency of the CPA, and that's it. We also observed that the continuous wavelet transform almost always improved the results of the attacks, and we also had higher gains for EM attacks, and maybe this is because of the higher frequency content of the EM leakage. On the discussion of the target, we observed that the impact of the higher clock speed was present for the NXP. We had 3.5 times. We needed 2.5 times more traces at higher clock speed, but this is not the case of the STM. And we also want to mention that there's no particular challenge for sapling these clock speeds. And to end these discussions, the NXP countermeasure, we have performed multiple tests, but we observed no noticeable difference in the attack results, and this was confirmed by independent teams. So let's end this talk with some conclusions. So our question was that how does the obscurity help in the case of unprotected hardware coprocessors? And we see here that obscurity did not prevent these side channel attacks. However, these side channel attacks are also non-trivial because they need more than 1,000 traces to succeed. And we also see that as they do not provide side channel security, these coprocessors should only be used to accelerate these computations, and therefore their natural direction is to use them in leakage resilience modes of operation. So thank you very much. And that's the end.